So this is the fourth tutorial in power system for this year. We have medium and long transmission line problems that we are going to discuss today. So the first problem that we have is a three-phase transmission line have been given certain parameters. What are the parameters given to us? We have been given the resistance of each conductor, that is 20 ohms. Now remember here we have a three-phase system. So when you have three-phase system, it basically means that you have three conductors. However, whenever the parameters will be given, that is resistance, inductance or capacitance, that will always be given per phase basis, that is only for one conductor. So here, since the resistance is 20 ohms, it means it is the resistance of only one conductor. Similarly, the inductive reactance, that is XL, is given to us, that is 40 ohms. This is also per phase. Sometimes in the problem, instead of XL, the inductance value will be given L. Then in that case, the XL has to be calculated, which is equal to XL is equal to omega L, where omega is equal to 2 pi f. That is the frequency in hertz. However, here XL value is directly given, so we need not to convert that. The capacitive reactance with respect to neutral is given, that is 4 into 10 to the power 4 mho. Now understand, when you have a three-phase system, you will have three lines and one neutral, and obviously the neutral will be grounded. So whenever the capacitive susceptance will be given, it will be between a line and the neutral point. If it is given between the two lines, the capacitance is given between the two lines, then in that case we have to get the value of capacitance of line with respect to neutral. Why we are doing this? Because we need to solve all the problems per phase basis, single phase basis, and single phase basis we always have between the line and neutral. So since the problem has to be solved in single phase basis, we have to do this manipulation. Then otherwise, sometimes capacitance will be given, then in that case you have to find out the value of Xc, which is equal to 1 by omega C. Here we have been given directly the value of capacitive susceptance. Susceptance is the reciprocal of the capacitive reactance. Load at the receiving end information is given. So the information is given about the load that is connected at the receiving end, that is 12.5 MVA. So note down the unit of the power, it is MVA, which means that it has been given the magnitude of the complex power, and it is given 0.8 power factor. So the power factor of the load is given to us, which is lagging in nature. By using the nominal T-model, you have to calculate certain parameters. What are they? Sending end voltage, current and power factor. That is, for the sending end, you have to calculate the voltage, current and power factor. You have to calculate the regulation and efficiency of the line. So this is the problem first. Let us see the solution. We have to solve this problem by nominal T method. So first we have to solve by nominal T method. So if you have the T method, you will be having the circuit like this. So this one will be Z by 2, this one will be Z by 2, and here it will be the admittance Y. So this side you will be having the sending end voltage, and this side you will be having the receiving end voltage. Now you can see that on the series side, the impedance is divided by 2. So we are having Z by 2, where Z is equal to R plus J time X, and we can write here XL. Now in the problem we have been given the resistance is 20 ohms and inductive reactance is 40 ohms. So we will be dividing that into two halves, that is we will be having Z by 2 here and Z by 2 here. So resistance will be 10 ohms on each side, and XL value will be 20 ohms on each side. However, the admittance part, that is the shunt part, will remain the same, which is 4 into 10 to the power minus 4. The power factor of the load at the receiving end and other information is given. If the receiving end voltage is 66 kV, so here the receiving end voltage is given 66 kV. Now this voltage is basically the line voltage. Whenever the information is given, that is the line voltage, because it is a three-phase system. This power 12.5 MVA, that is basically a complex power or the magnitude of the complex power. which is known as the apparent power. We have to calculate the parameters now. Now let us see how to solve it. We will apply the concept of KVL and KCL to solve the problem. Kirchhoff's voltage law and Kirchhoff's current law. Let us give some notation. If IS is the current which is coming from the sending end voltage ES, IR is the receiving end current which is going to the receiving end side ER voltage, and the shunt parameter is having a capacitive current where the voltage is, we can write its EC. Now we will be using the KVL and KCL concept to find the parameters. Let us find the receiving end current first. Receiving end current will have two components. One is the real component, which is cos phi r component, and sin phi r component, because we will be having the current as the magnitude of the current with respect to some angle theta. Now here we have been given 0.8, which is the power factor of the receiving end, so we can use that. Now how do you find the current at the receiving end? So current at the receiving end can be found out from the concept of the power. So we have been given the power S is equal to VI, and here we can write VI conjugate. This is the formula for power. So the receiving end current which is flowing here can be found out from the concept of the power. So power at the receiving end we can write as 3 times voltage at the receiving end, current at the receiving end, multiplied with the power factor cos phi r. We can determine the value of the real power PR from the complex power S. Then we can have the receiving end voltage, which is 66 kV. This is given as the line voltage. So we can divide that with root 3 to get the phase voltage. The receiving end current we can determine, and cos phi r value is given to us. So we can get the value of IR is equal to 109.35 ampere. Cos phi r and sin phi r we can compute from the power factor, and then we can get what is the receiving end current. This is a complex quantity. Now we can apply the KVL in this particular loop. If we apply the KVL in this particular loop, we will get the voltage, that is VC here, is equal to the receiving end voltage VR plus the total drop in this particular line. So the drop is basically the receiving end current into Z by 2. So Z by 2 is R plus JX by 2. So we will be getting the voltage of across this capacitor VC. Now we can find the magnitude of this voltage. So when we have a complex quantity X plus JY Z, then we can find the magnitude is equal to X plus X square plus Y square. So we can find what is the magnitude of this using the calculator. Now once we have got what is the voltage across this capacitor, now we can find what is the current which is flowing through this capacitor. So current is equal to voltage into admittance. So we have been given the admittance of the line, that is the shunt parameters. So we can find what is the current which is flowing through the capacitive end. Now we can apply the KVL concept here in this particular loop, and at this particular point we can apply the KCL, right? So the sending end current will be distributed in the receiving end current plus the capacitive current. So we can find what is the sending end current, because receiving end current and capacitive current we have already found out. Now the sending end current magnitude we can find out from here. Okay, once we have got what is the magnitude of the sending end current, it means we can get the value of alpha, which is basically 10 inverse of imaginary part of the sending end current, which is 49.483, by the real part of the sending end current, which is 87.0426. We'll get 29.62 degree as the value of alpha. Now if we apply the KVL at the sending end, we will be having the sending end voltage is equal to the capacitive voltage plus net drop in this part of the line, which is R plus JX by 2. So we will be getting the sending end voltage. Now the magnitude of sending end voltage we can compute from here, and then we have to transmit the computation in the line quantities. So the line voltage will be equal to root 3 times the phase voltage. So we have computed the phase voltage here. Now if you multiply that with root 3, we will get the line voltage of the sending end with its magnitude. Now we can compute the value of beta. Beta is nothing but the angle which is determined from the Vs. So the imaginary part by real part, we will have 10 inverse. So that is giving us 3.18. Now we have got the value of beta, we have got the value of alpha. This we are going to use it. Now after that, the sending end angle will be equal to alpha plus beta. So alpha and beta we have already computed. So that is 32.8 degree. It means the sending and power factor cos phi s is cosine of this angle, which is equal to 0.8406. Now the regulation, first thing that we need to determine. Regulation is basically the voltage of the sending end, that is the magnitude, minus voltage at the receiving end, magnitude, divided by voltage of the receiving end, magnitude. So we can substitute all the values which we have got in the calculation and then multiply it with 100 to determine in percentage. So that is equal to 10.76% the regulation of the line. This regulation of the line should be as low as possible, then the system will be better. Now the power loss we have to calculate. We have 3 conductors, and so we will be having 3 times I square R as the loss in the conductor. However, this current is distributed in 2 parts. One is the sending end part, another is receiving end part. Also, the power loss will be calculated only in the resistive part, because we have Z is equal to R plus JX. This part will not be considered in power loss. Only the resistive part will be considered. So on R by 2 on the sending end and R by 2 on the receiving end, that will be considered for calculating the power loss. So we are having some power loss that is determined. Then we can determine the line efficiency. Line efficiency is power output by power input. So power input can be written as power output plus losses. We have been given the power output from the load end. So the load is ZL, whose power output is given, so that we can determine from the value of complex power. So the magnitude of complex power, apparent power, multiplied with the power factor S cos phi. So we are getting the numerator value. Now in the denominator we have losses adding up with the output power, and losses we have already calculated. So we can put the losses multiplied with 100, that will give the efficiency of the line. So efficiency is 93.8% that we have calculated. Next problem, you have to determine the efficiency and regulation of a 3-phase 100 km 50 Hz transmission line delivering 20 megawatt. Now here you see it is 100 km transmission line. When the distance length of the transmission line is more than 80 kilometers, it is considered as medium transmission line. If the length is less than 80 kilometers, then it will be short transmission line. So we are dealing the problem for medium transmission line. So the power factor at the receiving end is given 0.8 lagging and 66 kV to the balance load. Now the system is 3-phase. So this voltage 66 kV is basically the line voltage at the receiving end. The power 20 megawatt is basically, now you note down the unit, it is in watt, right? If the unit is in watt, we are given the real power. So real power at the receiving end is equal to 20 megawatt. Now this is for 3-phase system. Okay, we have to convert that in single phase, which is equal to 20 by 3. Power factor information is given. The conductors are made up of copper and each having a resistance value of 0.1 ohm per kilometer and 1.5 centimeter outside diameter. Now here the resistance value is given in ohms per kilometer per phase, because always the component will be given per phase basis. The conductor diameter is given 1.5 centimeter. Now here the length is given in kilometer and diameter is given in centimeter. So we have to convert each quantity into 1 unit. So we can convert this 100 kilometer into centimeter first, and then we can do the calculation. And it is spaced equilaterally 2 meters between the center. Now here the unit meter is given, so we can convert that into centimeter to find that. Now neglecting the leakage and other factors, we have to determine the nominal T method and nominal Pi method, the efficiency and regulation of the line. So let us see the solution. So total resistance of the line first we have to calculate. We have been given 0.1 ohms per phase, which is multiplied with the total kilometer of the line. That will be 10 ohms. So 10 ohms is basically the total resistance of the line. In the previous problem, we were given ohms per phase, but no information is given for the length of the line. It means this is basically the total resistance. But here it was given ohm per kilometer, then it has to be multiplied with the length of the transmission line. So that is equal to 10 ohms. Now the inductance of the line we have to calculate because we need inductive reactance, that is XL. In the previous problem, the XL value was directly given to us. Here the XL is not given. So we can use the formula that we have studied in the previous tutorial, that how to find the inductance of the line. That is equal to 2 into 10 to the power minus 7. And then we have the length of the transmission line. And then we have ln of GMD by GMR. Okay. Now here we have been given 100 kilometers. So we will be converting that into same unit. Otherwise there will be a mistake. So we are getting the inductance of the line. Similarly, after getting the inductance, we can calculate the XL, that is inductive reactance, is equal to omega L, and that will be converted into ohms. Next, we will be calculating the capacitance of the line. C. The capacitance of the line will be calculated using the formula of 2 pi epsilon naught ln of GMD by GMR. So that will give 0.9954 microfarad as the capacitance of the line. Now we use the nominal T method to use. So here we can find what is the value of XC. XC is equal to 1 by omega C. That calculation also we are going to do. And then we will be having resistance, inductive reactance and capacitive reactance, XC. So XC will be the shunt parameter, that is Y, and R and XL will combine together, R plus JXL, to get the series impedance parameter. So in nominal T method, we will be having the Z by 2 component on each side, and on the shunt parameters we will have the capacitor, right? Now we have to determine the regulation and the efficiency of the line similar to the previous case. So first we will find the receiving end current. If you remember, in the receiving end component in the previous problem, we were given the component as MVA, right? Now it is given megawatt. So this is basically the apparent power, this is basically the real power. So we are using the concept of real power to determine the value of the receiving end current IR, which is 218.68. So we can use the formula power is equal to root 3 times line voltage into line current multiplied with the power factor of the load. Or otherwise we can write 3 times the voltage phase voltage phase current multiplied with power factor of the load. When root 3 is used, we will be using the line voltage and line current. When 3 is used, we will use the phase voltage and phase current. So here we are using root 3. So 66 kV is the line voltage that we have used. So 218.68 ampere is basically the receiving end current. Now we can compute the receiving end voltage. So receiving end voltage, we have converted that into phase component by dividing with root 3. So we have got the value of IR and we have got the value of VR. Now we will be taking the VR as the reference. What is the meaning of taking VR reference? That VR angle, the angle of VR will be equal to 0 degree. Then we will calculate the other parameters. Like for example, if we want to calculate the voltage of the capacitor, this one, if we want to calculate, then since we have already determined IR and VR that is given to us, we can determine VC using the KVL in this particular loop. So the voltage of the capacitor is the voltage of the receiving end plus net drop in this line. So we are having this value as the voltage of the capacitor, which is having a real part and the imaginary part. Now the current we can calculate. So current is basically value of voltage into admittance. So we can calculate the value of the current passing through the capacitor from this value, where admittance is equal to 1 by impedance. Okay, so we will be getting the value of the capacitive current. Now we can apply the KCL at this particular node. Okay, so sending end current is coming from here and then it is distributing in capacitive current and receiving end current. So we will be getting what is the sending end current, which is 210.57 amps, because we have been given the current of the capacitive current and the receiving current that we have already calculated. So we have got the sending end current. Now we can apply the KVL in this particular loop. So the sending end voltage is equal to capacitive voltage plus net drop in this line. So we have get value of Vs and its magnitude we have determined. So we have determined the value of Vs magnitude. Now we have to determine the no load receiving end voltage. What is the value of VR under the no load condition? So how we can calculate this? We can calculate from the voltage division rule that we know from the electrical science concept. So if we have been given the value of voltage Vs, then we have this one Z by 2. Here we have the admittance Y. Next we have Z by 2. Now we need to calculate what is the voltage VR here. Okay, so the concept says that the no load receiving end voltage, here the concept is under no load condition. If it is no load condition, no current will be flowing this side. So the current at the receiving end current will be zero. There will be no current flowing. So whatever the voltage will be there across this capacitor, the same voltage will be across this load, that is at the ending terminal where there is no load. Okay, so that we can apply the concept of voltage division rule. So the voltage of the capacitor is equal to Vs multiplied with the impedance of this part, that is I can say the impedance Zc divided by Z by 2 plus Zc. This is the voltage division rule. Now we have already determined the value of Vs. We have been given the value of Z by 2 and admittance. This admittance we need to convert that into impedance first, Zc. Then we can use this formula, and this is under the no load condition. So the voltage at the no load condition is basically 44746 volts. Now we can determine the regulation of the line. So regulation is basically the voltage at no load condition minus voltage at full load condition by voltage at the full load condition into 100. So voltage at no load we have determined. Voltage at full load is basically the receiving end voltage under the full load condition, that is already determined at the previously. So that will give 17.4% as the percentage regulation of the line. As I said in the previous problem, this has to be as low as possible. Now to determine the efficiency of the line, we need to determine the line losses. So line losses we have to determine Z by 2 component here and Z by 2 component here. So the resistive part of that is R by 2 here and R by 2 here. That loss we need to determine from the formula of I square R. So we have the current I square R. 3 will be multiplied because 3 conductors are there in 3-phase transmission line. So we will be getting 1.3824 megawatt as the net line losses for 3-phase system. This is for 3-phase system because we have multiplied that with 3. Now the total efficiency of the line is basically power output by power input. So this is the losses which we have added to power output. So that will give 93.5% as the net efficiency of the line. Now the same problem we have to solve by nominal pi method. So nominal pi method, we will be having Z here and we will be having Y by 2 and Y by 2. This side will be distributed in terms of admittance, and then we can apply the KCL and the KVL. So it is preferable to take the receiving end voltage as the reference phasor. So we will be taking the angle of VR is equal to 0 degree, which we have done in the previous problem also. So take the value of the receiving end current which we have determined previously. Now the current IC1, this we need to determine through the capacitor C1. That is basically the current is basically admittance into voltage. So we are knowing the receiving end voltage because the load will be connected across it. Here the load will be connected, and whatever the voltage will be there across the load, the same voltage will be there across capacitor C1 because these are in parallel. So we can apply the admittance into voltage to get the value of the current which is flowing through the capacitor C1, which is 5.95 amps. Now here we can apply the KCL at this particular node. If we apply the KCL at this particular node, that is, the line current will be distributed in the capacitive current and the receiving end current. So we will get what is the line current flowing, that is equal to 174.94 minus J 125.25. Now we have to determine what is the sending end voltage Vs. What is the sending end voltage Vs? Now we can apply the KVL in the entire loop, that is Vs is equal to Vr plus the net drop in this part of the line, because we have already determined the current which is flowing here. So we can apply the KVL to determine the total voltage of the sending end. After that, we can determine the magnitude of the sending end voltage. Once we have got the sending end voltage, we can apply the voltage division rule to get the voltage of the receiving end at the no load condition. So similar to what we have done in the previous, now only difference is that we have here y by 2 here and here also y by 2, and this part we are having the impedance Z. So under the no load condition, no current will be flowing here, that is the receiving end current will be 0. So whatever the voltage will be there across the capacitor C1, that will be the voltage of the load at the no load condition. Now we are already knowing the sending end voltage Vs, so we can apply the voltage division rule here in this particular loop. So we'll get 4762 volts. Now the regulation is voltage at the no load condition minus voltage at full load condition divided by voltage of the full load condition multiplied with 100. So that will give 17.47% as the net regulation of the line. This again has to be as low as possible. Now we have to determine the efficiency. So we need power output is already given to us. We need to find the losses. So the net losses in the line we have to find out, that is depending upon the line current. So line current we know. So line current square multiplied with the resistance R multiplied with 3 times because it is a 3-phase system. So we are getting 1.388 megawatt as the net loss in the line, and then the efficiency we can calculate by the formula power output by power input. So we'll have 93.5% as the net efficiency of the line. Next problem, a 3-phase transmission line of length 300 kilometers. Now you see the length of the transmission is very high, that is 300 kilometers. So we can think of this line to be a long transmission line, has an impedance given and admittance given, which is supplying a load of 50 megawatt. So the unit is in megawatt. It means this is basically given the real power of the 3-phase system for the receiving end. Now the voltage is 220 kV. So this is given the receiving end voltage of the 3-phase system, which is basically the line voltage, and 0.8 power factor. You have to determine the sending end voltage and sending end current. The system is 3-phase. The impedance and admittance are given to us. We have to solve the problem of long transmission line. So we have long transmission line, and this problem we have to solve by rigorous solution. So this is the formula that we have to use to determine the value of the sending end voltage and sending end current. So we have to remember this formula. Sending end voltage and sending end current we will be getting in terms of the receiving end voltage and receiving end current. So this matrix A is basically what we have to remember. So it is equal to cos of H gamma L, that is the propagation constant multiplied with the length of the transmission line. ZC is basically the characteristic equation, characteristic constant sin H gamma L. Here we have 1 by ZC sin H gamma L, and here we have cos H gamma L. So these two quantities are equal, cos h gamma L and cos h gamma L. This we have Zc sin h gamma L. Here we have 1 by Zc sin h gamma L. Okay, so we need to get the value of gamma, that is propagation constant, and we need to get the value of Zc, that is characteristic constant of the line, that we need to get. Okay, let us see how to find that. So first, from the load information, we have been given the load information ZL, right? From the load information, we have to get what is the receiving end voltage per phase. Always the three-phase system will be solved per phase basis, and then the result will be transmitted to three-phase system again. So the voltage of the receiving end per phase is basically the given voltage at the line end, at the receiving end, divided by root 3. So that will be 127.01 kilovolt. Now the power factor at the receiving end is 0.8. So we can determine the angle of the receiving end, that is the angle between the voltage and the current, which is 36.86. Now from the load information, that is the load power information, we can determine the receiving end current per phase. Now here we have used the term 3, then we have to use here the phase voltage only. So we will get the receiving end current per phase is equal to 164.02 ampere. Now we have taken the reference as the receiving end voltage. So the receiving end current in complex quantity we can note down. So this is the magnitude 164.02, and we can get the angle is 36.86, and since we have a lagging power factor condition, we will have a negative sign. So current will be lagging the voltage by a negative sign here, 36.86. Now we have been given the impedance of the line and admittance of the line. Z and Y we have been given. So that we are converting in polar coordinate first. Once we have converted the polar coordinate, this is the very important equation, that is the characteristic impedance of the line Zc, which is equal to under root of Z by Y. So we have to calculate under root of Z by Y. So we are getting this value. Okay, now we need to calculate what is gamma L. Okay, so gamma L is basically the real part of this equation, and the imaginary part will be equal to beta L. Okay, so we have Z equal to gamma L plus beta L that we need to calculate. So gamma L and beta L, now this is in radian. Okay, gamma L and beta L are in radian. So cos of h gamma L and sin of h gamma L we have to calculate, because we know that we need to obtain the matrix cos h of gamma L. Here also we have cos h of gamma L. Here we have Zc into sin h of gamma L. Here we have 1 by Zc sin h of gamma L. So these cos h gamma L and sin h gamma L we required. Okay, so we have to determine that, whereas the gamma L is basically alpha L plus J times beta L. L is the length of the transmission line. So we can write gamma is equal to alpha plus J beta. Now this is multiplied with the length, so this will be also multiplied with length. Now we have to keep the calculator in the radian mode here to do the calculation. Usually the students commit mistake by keeping that in degree mode. So you have to keep the calculator in radian mode here. Cos h alpha L plus J beta L, that we can break up into the trigonometric form, cos A into cos B plus J into sin A into sin B. Okay, and we have to put the appropriate values of that. So we will be getting the answer of cos h gamma L. Now these we need to convert in polar coordinate by keeping the calculator in the degree mode. So here it will be in radian mode and here it will be in degree mode. So we'll get 1.19 in degrees and magnitude is 0.9383. Similarly, sin h gamma L, we have to first keep the calculator in the radian mode and compute sin h of alpha L plus J beta L, which is sin A into cos B plus J times cos A into sin B component. Okay, and then we will be getting this complex quantity. Calculator you have to keep in here, you will be keeping in degree mode here to obtain the value of this degree, that is the angle of the sin h gamma L. So we have got the cos h gamma L and sin h gamma L. Once we have got that, now it is easy for us to find the sending end voltage and the sending end current from the concept of the constant that we have obtained. So these matrix we need to obtain A matrix, okay, and then we will be having the receiving end voltage and receiving end current. So these information we need to determine. This information is already given to us. So this is already given to us. So that will give you the sending end voltage and sending end current. So cos VR cos h gamma L plus IR ZC sin h gamma L. So we need to determine here using this formula to for sending end and receiving end component. So this calculation we are doing by rigorous solution. In short transmission line and medium transmission line, we are going by lumped parameters. Okay, lumped parameters. Whereas in long transmission line, we are going by rigorous solution where the parameters are distributed. Next problem. We have a single circuit 50 Hz 3-phase transmission line. The resistance, inductance and capacitance per kilometer of the transmission line is given to us. The voltage at the receiving end is 132 kV. Now this is a 3-phase system, so this is basically the line voltage. If the line is open at the receiving end, open means the no current is flowing through the receiving end current. Find the RMS value and phase angle when the incident voltage to neutral at the receiving end you have to calculate. The reflected voltage to the neutral at the receiving end you have to calculate. The incident and reflected voltage to neutral at 120 kilometers from the receiving end. So if you have this transmission line, here you have the receiving end VR. So here you have to calculate the incident voltage and reflected voltage. And 120 kilometers from here, 120 kilometers, you have to calculate here what is the incident and reflected voltage. So first we need to calculate the series impedance per unit length of the transmission line, that is Z is equal to R plus JX. So resistance and inductive reactance are given to us. We can obtain the series impedance. Shunt admittance is basically J omega C. So we will be getting the shunt admittance of the line. These are coming from the long transmission line. So per unit length we have used. Characteristic impedance we have seen previously, which is equal to under root of Z by Y. So series impedance by shunt admittance, taking the square root, we will get the characteristic impedance. Then we can determine the propagation gamma, which is under root of YZ. So we have been given the value of admittance and impedance, take the square root of that. So alpha plus J beta we can break up, whereas the real part is alpha and the imaginary part is beta. So alpha and J beta we have already got it. Now the receiving end line to neutral voltage VR. Okay, so we have been given 132 kV system, so that we divide with root 3 to convert into single phase. So we are getting 76200 volts. Receiving end current is 0 because it is under no load condition, and the formula for calculating the incident voltage at x equal to 0, because we are calculating from the receiving end. So here it will be x equal to 0, and here the x will be equal to 120 kilometer that we need to calculate. So the formula is VR plus IR ZC by 2, that is the incident voltage. The current is 0, so we are having VR by 2 as the incident voltage that we need to obtain. So VR is equal to 76200, so that will give 38100 as the incident voltage. And reflected voltage will be VR minus IRZC by 0. Again IR will be 0 here. Now here we have a positive sign, here we have negative sign for a reflected voltage. That will be equal to VR by 2 because the current is 0 at the receiving end under no load condition. So both incident voltage and reflected voltage are same under the no load condition. Now what happened when the distance is 120 kilometer from the receiving end? So VR plus is the incident voltage that you have to calculate two parameters, VR plus and VR minus. Okay, the formula is the receiving end voltage exponential alpha x plus exponential j beta x, where x is equal to 120 kilometer. We have to substitute. We know the value of receiving end voltage, we know the value of alpha, we know the value of beta, x equal to 120. So we'll get VR plus, and here we have the negative sign in exponential term, we'll get VR minus. So because a wave will have a positive sign and wave will have a negative. Okay, then we will be getting the reflected voltage at a distance of 120 kilometer from the receiving end, which is, so this value will be 78.7. So 78.76 by 2 angle minus 8.0. This is reflected voltage. This is incident voltage. So we will get 36.85 angle minus 3.02 kilovolt. Now, what is the incident voltage at a distance 120 kilometer? So from these information, we have to calculate that. That is equal to 78.7 minus 2. So we are having VR plus VR minus divided by 2, or otherwise VR plus divided by 2 we are having. Okay. So that will give us the incident voltage at a distance of 120 kilometer from the receiving end. So this way we can calculate both incident voltage and reflected voltage. Next problem, the inductance and capacitance of a 400 kV three-phase system. So this is basically the line voltage at the receiving end. Okay, this information is given line voltage at the receiving end. 50 hertz lossless transmission line. Lossless means there is no loss, so we will be not having any resistance part or any conductance part. And this information is given about the inductance, and this information is given about the capacitance of the line. You have to find the surge impedance and surge impedance loading. So you have to determine what is ZC and what is the power surge impedance loading of the line that we have to calculate. When the line is delivering 210 megawatt to maintain a voltage of 400 kV at the receiving end. So here you have the receiving end voltage. Which type of compensation is required? So what type of compensation is required? You know, compensation is just basically improving the power factor of the line. So this information we have to calculate for 210 megawatt, and in the third case we have 620 megawatt at the receiving end, maintaining the voltage at 400 kV. So what type of compensation is required? So these are the two, case 1 and case 2, that we have to solve. So two cases will depend upon the first one, that is the surge impedance and surge impedance loading. So let us see how to solve this. So from the information of inductance and capacitance, the first we will calculate the surge impedance. Surge impedance is the characteristic impedance, which is under root of L by C. Once we have got the surge impedance, we can determine the surge impedance loading. So what is the power? That is the voltage at the receiving end square divided by the characteristic impedance or the surge impedance. So here we have 389.24 ohms that we have to put. Receiving end voltage is 400 kV. So we will get 411.05 megawatt as the net power of the surge impedance loading. So these two quantities we have to calculate first from the parameters given to us. Now two cases are there. One is 210 megawatt and another is 620 megawatt. 210 megawatt is less than the power of the surge impedance loading, which is 411.05. It means there will be a voltage drop occurring in the line, and in order to maintain a constant voltage of 400 kV at the receiving end, we required shunt inductive compensation because it is less. There is a voltage drop. However, in the second case, when 620 megawatt is greater than the surge impedance loading of the line, to maintain a constant voltage at the receiving end, which is 400 kV, we required a shunt capacitor compensation. So in the previous case, we required shunt compensation. Here we required shunt inductive compensation. Here we required shunt capacitive compensation of the line. Next problem. We have a 220 kV 220 kilometer transmission line. Calculate the receiving end voltage under no load condition, considering full capacitance value. Reduce capacitance value to half of its actual value. Let us see how to solve that. Sending end voltage is given 220 kV. Length of the transmission line is 220 kilometer. These two informations are given. We know that the sending end voltage and Vs and Is relationship, that is the sending end quantity with respect to the receiving end quantity, that is the receiving end voltage and receiving end current, can be given by the ABCD parameter of the transmission line. Now we can get the Vs value of the sending end in terms of ABCD parameter. So C and D will not be involved here, only A and B will be involved. Receiving end current is 0 because load is not there. So we'll get the receiving end voltage is equal to sending end voltage divided by the parameter A, right? So nominal pi method, if we apply, then A is equal to 1 plus yz by 2. This we know from previously that for a nominal pi method, the value of A is 1 plus yz by 2. And the line is lossless. So R and G is 0. That is resistance and conductance is 0. So we can substitute the value of Y and Z in this particular line. Okay. Y, that is the admittance, and Z, that is the impedance. So Z is equal to XL and Y is equal to XC. That we need to substitute in the value of A. So A will be equal to 1 plus yz by 2, and then we can apply little bit of mathematics here to find what is the final result of A. So A we will be getting 1 minus omega square L square by 2 nu square. Now what is this nu? Okay, what is this nu? That we will see. Omega is the frequency, L is the length of the line, and nu is also a constant which is the velocity of the light, and it is given by 1 by under root of LC. It is 3 into 10 to the power 8 meter per second. This is a constant quantity of the velocity of light. It means that if we put that in a formula that we have got in the previous case here, then we will get what is the constant A here. It means we will get the receiving end voltage which is equal to Vs by A. So receiving end voltage is 224.93. What we are finding that receiving end voltage is greater than the sending end voltage. So we are getting the VR value is greater than Vs. This effect is known as Ferranti effect. So Ferranti effect says that under no load or light load condition, the receiving end voltage will always be greater than the sending end voltage, which we have validated here also. However, let us see what happens when capacitance value is reduced to half, that is C by 2. If capacitance is reduced to C by 2, we'll put it in the A parameter here, and here it will be C by 2. Rest will be same. So we will be getting the value of A first, that is 0.986, similar to previous case, and then the receiving end voltage. So here we have 223.12 kilovolt as the receiving end voltage when the capacitance is reduced to half. So this complete the tutorial 4th, that is on medium and long transmission line.